which will typically be on the right because you added it in last, so it'll show up on this side of the window, so on the right. So the data analysis toolkit that we added is for financial and scientific data analysis, which includes what we use in psychology. So what you do is when it's added in, you can click on it, and it will show you a window that has all the formulas we need, all in one place. So it makes it very easy for you. Okay. They're all in alphabetical order. Okay. What I ask you first is to run descriptive statistics on all the data. Okay, so anytime you do statistics, you have to start with your descriptive stats. And then you should run descriptive stats on all your information, okay, before you go and do inferential statistics. Because what you're looking for is to get the mean, the median, the mode, to make a decision, oh, is this a normal distribution or not? It's really important that you make that decision before you run inferential statistics, because the inferential statistical tests that we use in psychology are only used when your data follows a normal distribution shape. If it's skewed, then you have a problem. Then you might have to collect more data, because that's one of the inferences, one of the rules. You can only use these tests if it's on a normal distribution. And how do we figure that out? We have to run descriptive statistics. Okay? We just want to make sure there's not a lot of outliers, extreme scores, either really low scores or really high scores. If you end up with descriptive statistics that are really skewed, that means that if the mean and the median mode are not near each other, you may have to exclude some pieces of information from your data to make it more normal. Okay? And that, again, if it doesn't, it violates one of the assumptions of using inferential statistical tests, which means you're not going to get accurate results. Okay, so let's just say that everything's fine. So I have the assumption that it is a normal distribution. So let me run my descriptive statistics to assure me of that. So what you do is go ahead and click on descriptive statistics, and then you hit OK. Then Excel, there's going to be window upon window. Like every time you click something, another window will open. Then you click that, another window opens. Okay. So in the input range box, what it's asking you to do is to highlight the information you want the computer to run the descriptive statistics. What data do you want the computer to go ahead and calculate the mean, the median, mode, and the standard deviation, and the range? Okay, so measures of central tendency along with measures of variability. What information do I want the computer to use? So these windows, you can move them around because you're going to have to click back into the data set to highlight the information. You can do it ahead of time, but it's usually easier if you do highlight the function that you want and then highlight the data afterwards. Okay? So let's just say I'm going to highlight the data here. Let me explain what this is. Okay, on the left, what I have is in the first column, you see it's labeled gender. Okay, so in Excel, when you put information, you should group different variables by columns, and each row is a different participant. That's how you should group your data. So when you are doing your project, when you're inputting your data, remember, you need to create a new column for each variable, and then each row is the same person's information all the way across those variables. Okay? So in this case, I have the first column is their gender, and then I have it by their age. And then I have their scores on, if you remember what that abbreviation stands for, it's the Rosenberg Self-Esteem Score, along with their score for the Cooper-Smith Self-Esteem Inventory, which are the most two commonly used self-esteem scores in research, and they're pretty valid and reliable. So what I did was, over the years, I started taking your scores and putting them into a data set to use for this assignment. So this is actually real data from past students. And so it's their score in the Rosenberg and then their score in the Cooper-Smith inventory, or the self-esteem inventory, that's what SEI stands for, self-esteem inventory, and see if there's a correlation, to see if there's a linear relationship. But first I just want to run descriptive stats. I just want my measures of central tendency, and I just want my measures of variability. So what you can do in Excel in the input range is when you're doing descriptive stats, let me include age as well. You can highlight all the columns together, and that's why it's important that you group them next to each other. Because in Excel, you can, if you highlight all the columns together, you don't want to highlight empty columns, okay? So they're grouped by columns, so I just double check that in my window. Are they grouped by columns or are they grouped by rows? You can actually do by rows, but it makes more sense to do it this way because all the default settings in Excel group variables by columns. And then what you could do is click this label here, or this option here, labels in the first row. Because it's telling the computer, don't use the first row as a case or a piece of data to calculate descriptive stats. One, it's not numbers, and two, it's a label. So when you actually calculate the descriptive stats, it'll label it for us. Okay. So make sure if you do highlight the labels, you actually click labels in the very first row, and that's why we usually do that. Do the labels first, and then put the data underneath it. It just makes a lot more sense. Now, what if you accidentally didn't include labels in the first row? You just need to make sure what column came first, because it'll spit out that data that way. So if age was the first column you highlighted but forgot to put the label, that's the first output that's going to come. You could actually do the columns separately if you wanted to do it that way to keep it all. I mean, if it's too confusing to do all at one time, you can highlight the columns separately, like one at a time. It just takes more time that way. Okay, so input range, I highlight the 3 columns that I want descriptive stats on, and then I put labels in the first row just to make sure that they don't include them. They label what they call output is what they generate. Okay, what's the outcome of the stats? And then for descriptive stats, there's one more step you need to take, because if you don't, it's not going to give you the information you need. You need to make sure you click on this option down below called Summary Statistics. It will include the measures of central tendency and the measures of variability that you need. So the mean, the median, the mode, and standard deviation, variance, range. Okay? So highlight the columns, make sure it's grouped by columns, highlight or click labels in the first row, then make sure to select Summary Statistics on the bottom, then you're good to go before you can hit OK. So when you do all that,
and keep the new worksheet PLY.
Yes, you can, okay. So there's a couple of things you can do. If you want to highlight an output range, meaning you want to designate where the output is located, like if you want it on the same sheet, you can actually go like this, and then highlight empty cells, and then it'll return the information there. Okay. I like to do a new worksheet in the same data set, because if you somehow if you do this on campus and then you want to send it to yourself, you just need to send the one Excel spreadsheet. You don't have to send multiple spreadsheets to yourself. So what I like is to keep them separate, and then you could label this sheet with tabs, like descriptive stats, and then you could do a t-test and then a correlation. That's why I like to keep it as the new worksheet. Okay? So we'll do the new worksheet, we'll keep it like that, and then I gotta go back because I highlighted blank cells, so I gotta make sure that my input range actually is this, what I want you to run descriptors. So you actually run descriptors on all your variables. Unless it's nominal, don't worry about that. Okay, it has to be quantitative. So labels in the first row, new worksheet, not new workbook, and then summary stats, and then you can hit OK. This is the easiest way to do it if you're really good at Excel. Okay, these are very simple and basic commands. You don't have to be, like a genius at it. Okay, I'm not. So if you did it correctly, here's what you get, what we call the output. Or, in this case, the descriptive statistics we need, one, to look to see if our distribution is normal, and two, as if you're writing a paper, this is what you would put in the paper, okay, in terms of the results, the information that you need. Okay, so let's just take age. Let's look at my mean score, 23 years old. You could round out to the nearest 10, so 23.3. Okay, so there's a lot of numbers, but what we're looking for is measures of central tendency first. So do we have the mean, and the median, and the mode? We do. The median and the mode are actually almost the same number, 20 years old. And it's not too far off 23, which is the average. Which you can say, okay, it's not too bad. It's probably normal distribution, because the mean age score, the median age score, and the modal are all around the same number. Okay? So 23 and 20.5 and 20, not too far off. If it was something like 23, then you had something like, you would have this because it's all 18 over, but you had a median of like 15 or something even lower. That means you have higher variability, but it also means that that the distribution may be skewed somewhat. Okay? So let's look at the standard deviation here, 6, which is kind of like on average, the mean score of like if you chose a random age of a participant, 6 years from the mean. Okay? But it's not too bad, okay, because if we look at the mean and median mode, they're similar, so we know that we have a somewhat normal distribution. And then if we look at the range, this is 24, because what it does actually take 42, which is the highest age, so the oldest person in the sample, subtract it from the youngest person, which is 18, and you get 24. But when I say I want the range, I actually just want those numbers, 18 to 42 years old, okay? Now, so there's a standard deviation here. So we have the mean, the median, the mode. Standard deviation and the standard deviation squared is the variance. Then you have the range, but what I really want is the lowest and the highest score. It tells you, the count is how many items you had or how many participants there were, so 56, so which is important, okay? So then if you go to the Rosenberg, it tells you the same thing. As a sample, here was the average for the Rosenberg, 22 we know is kind of high. So we know that's normal for a sample of collections for the Rosenberg. Remember, the closer it is to 30, the higher it is. And then look at the median, the mode, so 23 and 27. Not exactly the same number, but close to it. Okay, so somewhat of a normal distribution, maybe it's kind of skewed. For an average that's a little bit higher, maybe than normal. And then if you look at the standard deviations, even lower here, 4. So that just not too bad. We don't have too much variability here. So on average, here's how the scores deviate from the actual mean. Okay. And then, which makes sense because if you have 22 and then you add like almost 5 points, you get like 7, which is the modal, which means again, that's the one that frequently occurs the most, and it's close to 30, so again, kind of higher than average. But the range here is 19, but really it's somebody scored 11 and the highest score was a 30. So we have scores that fall into that range. Okay. Then the same thing for the self-esteem inventory. I think the highest you can get, I think is either 50 or 60. Let me look that up. But we have a mean score of 38, right? I think it could be 39, and then median of 40 and mode of 44. I think it's actually 50, yeah, because the maximum here was 49. So the range is 13 and 49. If you look at the standard deviation, okay, about 7 points on average. Scores deviate from the mean for about 7 points. It could go either way, below or above. Okay, so for the most part, we have distributions that when you plot it, it would look like this. It's not going to be perfect, but we can say, okay, now we can, since we haven't really violated the assumptions, we can do the inferential sets because this data, when you plot it, should have a normal distribution or this bell curve. Okay. And the reason why we like this shape is because if you take any characteristic that's physical, meaning like inches, height, if you had even this numerical, when you gather in a population, you're looking for average scores. You actually, when you plot it, will fall under this shape. So that's why we use it. That's the assumption that all psychological traits follow that rule. Most physical traits, like how many inches of rainfall each year, that would fall if you actually calculate that information for anywhere in the world and plot it into a distribution, you get that shape. Okay? But it's the assumption that all psychological traits follow that rule as well. Okay? So you're going to actually go ahead and do that where you highlight descriptive stats, click labels in the first row, click summary statistics, and you get this. Now, did you see me when I did this? In Excel, you can change the width of the columns. So if you get this and you can't tell, you just need to expand it, which is important because the homework requires you to print all this information and bring it to class on Tuesday. So make sure that you expand the columns so you can see the labels. Okay? Because when I ask you to identify what's the mean score for age, you would have to put it into the worksheet. Okay. So what you can't do is here, when you run the analyses, you can actually click into the tab and then you can rename it. Okay. Oops. So you can go rename. So we'll just do descriptive stats. See how you can do that? Oops, sorry. You can do that. And it keeps everything organized for you. Okay. So you can scroll between the data, the sheets. Okay, the next thing that I want you to do, remember it's underneath directions. So run descriptors on each of the following variables: age, both self-esteem scores, and 3 groups in the memory test scores. So let me go back to this. Well, you can do that for homework, but it's the same thing. You would actually highlight them all together. It's 3 different groups on an experiment, which was basically 3 different ways of learning information. And we don't have to know like the 3 different ways. So just 3 different groups. And what was measured was how many words they remembered at the outcome of the study. And we're going to see if there's any differences between the 3 groups. Okay, so you can run descriptive stats that way. If you're really concerned about highlighting them all together and there's empty cells, just run them one at a time. Okay. The directions say after you run descriptive. So again, all you have to do for the homework is run the analyses that I ask you to and print them out, the output. You don't have to interpret it at that point. 2, run a correlation analysis on self-esteem scores. So both the variables in the data set, so go back to data for analysis. Remember I told you these are 2 self-esteem measures. The first one's the Rosenberg, which you're familiar with. The second one is the self-esteem inventory. When I want you to run a correlation, I want you to highlight both scores, because what we're looking for is if pupils on the Rosenberg, if they score higher, like close to 30, 27, what does that mean for their Cooper-Smith score, their self-esteem inventory? Does it also increase or kind of get to the maximum? So if I have a prediction that it's the same group of people, they took 2 self-esteem measures, if they're both valid and reliable, I would assume that there would be a positive correlation between the variables, meaning that if somebody scores higher in the Rosenberg, they're likely to score higher on the Cooper, or the self-esteem inventory. That's logical. Or you can say that if a score decreases on the Rosenberg, the score on the self-esteem inventory will also decrease as well. I'm just predicting that I can kind of predict one from another, but they are related in a systematic fashion. So I'm just saying, oh, as one goes up, so does the other. So how can I test that? So we go back to our data analysis function, or our quick tool there. Then I ask you to run the correlation. Okay? So go ahead and click correlation. Remember, it's all in alphabetical order. So what I do is I click OK once I highlight correlation here, and I say I actually want you to correlate the 2 variables together. In this case, they're both self-esteem scores, but in your project, they're going to be 2 different variables. They're not going to be the same like this. But they're different measures, so you're not going to yield the same results. Okay, group by columns, labels in the first row, because I did highlight the labels. New worksheet of the same file. So input range, make sure I highlight the 2 columns side by side. Typically, it's easier when you have them side by side. And then label the first row and hit OK. If you do it right, and if you, for example, highlighted the labels but forgot to hit labels in the first row, or somewhere included qualitative or non-quantitative data, it's going to return an error message. So that's why I said correlations can only be conducted on 2 variables, but both are measured in a quantitative fashion. Okay. So, and it labeled it for you. There's 3 numbers here. You're going to be looking at the number that's a decimal number. Because remember when I said the only thing that you'll never find a perfect correlation unless you correlate something with itself. So when I correlate the Rosenberg self-esteem score with itself, I'll get a correlation of 1. So what you're looking for is this number. This number is the actual correlation coefficient. This tells you how strongly these 2 variables are related to each other. The coefficient tells you if it's a weak, strong, or moderate, but also tells you the magnitude, okay, which we'll get into. So this is closer to 1. 0.7 is closer to 1 than it is to 0. So you can probably say, oh, it's a pretty strong correlation. But is it statistically significantly? Or if it's a statistically significant correlation, that's a different story. Okay, but usually when you have a larger correlation, it usually means that it's also statistically significant. Okay, so if you get that, that's another output, then you can label it down here. You could put, or do a right click, do rename, and you could do correlation. Okay? What you could do is, when you're done with doing all this, running all the analysis, you could actually highlight them all, let me go back to correlation, and then copy and paste them into one spreadsheet, and when you print it, you can save paper. Okay? You don't actually have to print out all the different ones, okay? Because it's going to waste a lot of paper. But you could do that, okay? Okay, so and you can shrink them too. You can actually copy and paste into Microsoft Word and shrink the table if you wanted, or PowerPoint if you're familiar with that. Okay, so if I go back to the directions, I did the descriptive stats, I ran the correlation, now I want to run a t-test and self-esteem scores grouped by gender. Okay, great. So go back to my data analysis. Okay, remember a t-test is for when you want to compare 2 groups on a measure. And you have 2 groups, in this case I asked for gender differences, so we use a t-test because it's only 2 levels of that. There's only 2 groups and there's 2 levels of gender in this case. Okay, so female versus males in my study, who has higher or lower self-esteem scores? But here's the important part. When you run a t-test, you are looking at the mean scores between 2 groups, but on the same variable. So you don't highlight between the 2 different ones. You pick one that you want to look at the differences on and stick with that. Okay, so what do I mean by that? For the homework, if you want to, we'll do both. So run 2 different t-tests on the 2 different self-esteem scores, grouped by gender, but I'll show you how to do it. So you go ahead and go to data analysis. You have to scroll all the way down to when you see t-test. Okay? So there's a paired 2 sample for means, a t-test for 2 samples assuming equal variances, and then another one, a 2 samples assuming unequal variances. Okay, there's 3 of them. Which one do I need, right? So you need to figure that out. I said that you only use the paired samples t-test when you have the same group of participants. You want for changes from time 1 to time 2. So that's not the problem here. So we can exclude the paired samples. So it's either a t-test assuming unequal variances or it's a t-test assuming equal variances. Which one do I need? Okay. If I say that I predict that there's going to be a difference somewhere, and I'm assuming that the difference has to do with gender, and those differences or the variance between the 2 groups of changes, or I'm sorry, the difference is brought about by being either male or female, I'm already saying I expect a difference because they're different already. So in that case, I would choose the t-test for 2 samples, so 2 different groups. I'm assuming they're already unequal because male and females are different, okay? So unequal variances. I would use the equal variances if you had a t-test and you're looking at 2 different groups, but in an experiment, you randomly assign them to either group. So therefore, you've taken away any differences ahead of time by using random assignment, and any differences in the beginning of the study are not going to influence the results. In that case, any differences are held equal. So in this case, for the gender, you use unequal variances. Technically, they're basically the same test, one's slightly more sensitive, but if you accidentally choose the other one, it's okay. We basically yield the same result. That's just the difference on this actual function. Now, there's 2 of them, which one do you use? Technically, there's one for specific conditions, but they're pretty much the same test, so if you accidentally choose equal variances over unequal, you should get similar results. So you should be okay in that case. But I'm already saying there's gender differences, so I choose t-test 2 samples assuming unequal variances, which is another way of saying this is an independent samples t-test. They're named. So there's all these different ways to refer to them, but they're basically the same thing. I have 2 groups. I want to see if they're different in some way, and I'm looking at their mean scores. Okay, so I hit OK. Now you have 2 input ranges. You have to put in one box, one group, and then highlight in the other box the other group's scores. Okay, because it's 2 groups, I have to make sure that I designate this is one group and this is the other one. How do I do that in Excel? Okay, so we're going to do both, but let's just start with the Rosenberg. I say, oh, I think there's gender differences. That males in my sample will report higher levels of self-esteem scores than females, but let me stick with one variable, so let me use the Rosenberg first. Okay, so what I'm going to do is this. I'm not going to click the label in the first row. I'm just going to click the numbers, and I'll tell you why in a second. In Excel, I've already sorted the data for you. I went ahead and put the females first, and then below them, I inputted the male scores, okay? And if, for example, in your data set, you like kind of just randomly inputted the data, you could sort the data, so it does that for you, okay? So if I say one of my groups is female, let me highlight all the female scores for the Rosenberg as a group. And then I'll go ahead and highlight all the scores for the Rosenberg self-esteem survey. But let me do the males second, okay? So how do I know? Just look at the gender column here. It'll tell you when to stop. So you can start there and keep going until, oops, there. I see M for male. So I just want to make sure that I include the last case that indicates that they're female in this input range, variable 1. So my first group is females, okay? And my second group, I'm going to put the males. Now, I'll go ahead and do that. So if I go back to the data set, I'll scroll down a little bit more. You can see that in these 2 classes, there was, I think, twice or 3 times as many females than males in the class. So in this case, when you're looking at that, the groups are going to be unequal because the numbers are unequal. So these rules might be a little bit skewed, but that's okay because we're just doing it for practice.
I think you have H highlighted.
Okay, sorry. Oh, I do. Let me go back. Thank you, Michael. Okay, so I'm going to go to the Rosenberg, and then let me do this first. I'm going to go to female. You could do age differences if you wanted to. I'm going to go back to this one. I'll go ahead and do that. Thank you. Okay. Once you're done with that, there's another step you have to take. The hypothesized mean difference asks you, what is the difference that you would expect to occur? What's the value of that difference? Now, this is according to the null hypothesis theory, which we didn't really talk about. But if the null hypothesis was true in this case, you would put a 0. So just go ahead and say that you're going to put a 0, and we'll explain why on Tuesday. Okay? So hypothesized mean difference is equal to 0. Leave the alpha Lambo as is, because we'll explain that on Tuesday. And then the labels, I didn't put labels because I wanted it to make sure that all the cases that I highlighted go into the actual formula. But if I put labels, it would treat the first number as an actual label. So don't hit labels, even if you highlight the first label, the label of the column, because when you go to the male scores, there's no label there. So just highlight the numbers, okay? That's why I did that. So I hit OK. And here's what I get. I get what they call the results of the t-test. Okay. Variable 1, and what's good about Excel is that you can go in and change the labels. So variable 1, remember I highlighted the female scores in here. I have the male, so I can do that to make it clear. The mean scores, again, the average score as a group. On average, if I look at them as a whole, the average score on the Rosenberg was 22.8 for the females. And for my males in the study, 22.3 or 22.4 around that. What does that tell you? Oh, their scores are fairly similar. That means they're actually pretty close. There probably is no difference between the two scores. So I want to check the variance. Oh, they're pretty similar. It makes sense. Okay. The number of observations are off, so this is kind of skewed because you have way more females than you have males. But again, this is for practice, so that's not a big deal. So you're looking at all these things. We'll explain what degrees of freedom is, and then we'll explain what all these numbers mean. Now, if you get an error message, you did something wrong. Okay? You should get a table that looks like this. So it's labeled t-test, 2 samples who meet unequal variances, and you get all this information. So this is what you need to print out. Again, if you get an error message, you did something wrong. So I'm going to do it again with the self-esteem inventory. You can practice the same thing. You could do both on the homework. Okay? Because, practice makes perfect. So let's just go back to the data. I'm going to run a t-test, exactly what I did. But I'm going to instead choose the self-esteem inventory scores, not the Rosenberg. But notice how I stayed within one variable. We can do, like, for example, I want to tell you the difference between the Rosenberg and the self-esteem inventory scores, then use a t-test. A t-test is used to look at the differences on the same variable, but in 2 different groups. Okay? So,
You want us to do this for the homework? Both of them?
yeah, you can practice. So we can do the self-esteem inventory for females, and then we can do the male. We just click into the box and go ahead and highlight the remaining items. Okay, don't highlight any empty cells. Hypothesize mean difference stays 0. We don't have to do labels because I know I highlight females first, male second, so I can just label that when I get there. Okay, and expand the column so you have all the labels. You can see everything. So we'll just put male, we'll to male. Perfect. Now, if based on the data from the last table that we got, if the mean scores were fairly similar on the Rosenberg, you can predict the scores on the self-esteem inventory will also be similar. So if we look at the mean scores, oh look, 38.6 and 30.8. Oh, they're pretty much the same. Good. This means that I did something right or I'm following direction. The variance is off a little bit, but we have all this information that we need. Okay? So based on just this, without knowing null hypothesis theory, you can probably say there is no gender difference because when I compare the male scores as a group to the females, their scores are the same, 22 versus 22 or 23 versus 38 and 38. Okay, so whether or not that's statistically significant, again, that's another way of looking at the data. But this is what this can tell you, kind of just by looking at it. Okay, so that's what you need to do for that one. That's a t-test. So we just ran a correlation. We just did a t-test, or we did 2. Now you have to practice doing an f-test, or an ANOVA, which looks at the difference between 3 groups or more. Okay. So what you go is you go back with some directions. Okay, run a t-test and self-esteem scores. You can do both by gender. Run a single-factor ANOVA on the memory test scores by all 3 groups. Okay. So let me go back and go to data for analysis. And remember, this is an experiment where I had 3 different groups. They had 3 different learning methods, and I tested them on performance at the end. One of the groups is almost double the amount, but that's okay. This is just theoretical. So, and an f-test is a little bit different. You have to put the scores, the columns next to each other, like you do a correlation, okay? but you actually have to highlight all the columns at once. So however you have it, just make sure that the computer knows. So you go back to data analysis. Now what's interesting is that there actually is an F-test for 2 groups, but we're doing an ANOVA for 3 groups. The one that you actually have to choose in the window here is called ANOVA single factor. The single factor means we're just looking at the differences in more than 2 groups, but on the same factor, on the same variable. In this case, performance on a memory test. It's the same thing on the same measurement, but I'm looking at the 3 different groups because they have 3 different learning methods or teaching methods. In that case, it's an experiment to see which teaching method is the best, okay? So don't choose F-test here. Don't choose ANOVA 2 factors with or without replication because that's not looking, it's not like a factor of factorial design. We're looking at 3 groups on the same variable, so we run an ANOVA. Now, a single factor ANOVA. If you had in your project 4 groups, like say birth order, but again, the difference is on the same variable, you choose ANOVA single factor. Okay? So it's the first one. There's all these other ones here, but don't worry about that. So this is the one for the project. You hit OK. Now here you would have to highlight it has to be all together because there's only one input range. Group by columns if you had a group by rows. Okay? Now it's important to know that these are all the cases or this is all the information. You actually don't put like the mean scores in your data set. You put all the information in. Okay? Then in this case I can hit labels in the first row because I do have labels there. And you keep the alpha level 0.05. And again, we'll learn why on Tuesday. Okay, and if I do everything right, I should get an ANOVA table, okay, which looks like this. The first table tells you the average scores and the variance, we should figure the standard deviation by squaring those numbers, between the 3 groups, and then it tells me what the outcome of the actual formula of the analysis. So we're looking at the differences between the groups, and so this is what that information tells us, whether or not those 3 groups differ in some way. Okay? Now, what I want you to do is, once you do this, you need to go back, and I need you to run additional t-test for the 3 groups. But you're going to have to run them 2 groups at a time. So you have to go back to data analysis. You go back to the t-test. Now, this was an experiment, so we randomly assigned students. So in this case, you can choose the equal variances because we're saying that there's no difference between the groups, and if any differences would influence the results because we randomly assign them. So if you choose t-test for equal variances, you hit OK. And I want you to look at the t-test between 2 groups at a time. So in this case, you can go ahead and do the comparison between group 1. Then here you can go group 2 and highlight all the cases. You can put labels, make sure it keeps the hypothesis significance at 0, and then you hit OK. And then again, it's just the results of the t-test. And then when you go back, you run the t-test on, so we just did group 1 versus group 2, and you go back and do group 2 versus group 3, and then another one, group 1 versus group 3, okay? So you're going to have to run actually 3 more t-tests in total, comparing the 2 groups, but make sure it's group 1 versus group 2, and then group 2 versus 3, and 1 and 3, okay? And that's basically your homework right there. So the important part is running all the statistics, putting all the tables, making sure they're all labeled, looks nice and neat. And then you print all of that stuff out and bring the output with you in class on Tuesday. If you don't bring it with you, you're not going to be able to do the worksheet, which is worth 50 points. And I basically tell you where to put everything and answer all the questions. But it only makes sense